Hello guys, welcome to today's lesson. And today we're going to begin the new topic 2.9, which is exponential and logarithmic functions. Today in particular, we're going to explore only the exponential function. And we're going to go over these 8 points, okay? Briefly. These are very simple because you already, like I tell you often, you already know these things. For example, domain and range, zeros, intercepts, asymptotes. You already know most of this. So since they are not new concepts, we can actually do this very quick. Okay, so let's start. Number one, let's talk about the definition. Oh, and by the way, everything is gonna fit in here. You're gonna see. So let's talk about the definition of what we understand as the exponential function. The definition is the following, guys. The exponential function is given by f of x equals a, which is a constant, raised to our independent variable, which is x, with some requisites or some constraints. Very important constraints. You should not forget about what I'm going to write next. With the constraint that a has to be greater than 0, and also a has to be different than 1, or a cannot be equal to 1. Okay, so that's the definition, guys. That's what it is. That's what we know as the exponential function. Some constant, which is greater than 0 and cannot be equal to 1, raised to our variable. What is the difference between these functions, say, and this other function? For example, if I wrote f of x equals x to the 3, what is the difference? I mean, both have exponents, right? This is an exponent, this is an exponent. Why am I calling this exponential function? And why is this not an exponential function? Well, because of the location of the variable. In here, the variable acts as the base of this number, and this is the exponent. And in here, the base is a constant, you see? And your exponent is your variable. So in this case, this is an exponential function. And in this case, if you remember, this is known simply as a polynomial function. So that's the definition. Done. Okay, now number 2, we're gonna discuss the peculiarity of the definition. What am I talking about in here? Why do I write this word, peculiarity, the quirkiness? Okay, I'm talking specifically about these two things, guys. Why are we ignoring, or why do we refuse a to be equal to 1 in this definition? This is my definition, right? Why am I refusing a to be equal to 1? Why am I discriminating against the number 1? And why am I also discriminating for all the negative numbers? If you see, by putting this requisite, by saying that a has to be greater than 0, I'm ignoring, or I'm refusing to work with any a that is negative. You see, in this case, for our exponential function, this number here cannot be negative nor equal to 1. Why is that? Why is that, guys? Okay, everything has a reason in mathematics, and the reason is as follows. The reason some mathematicians some time ago, and I mean a lot of decades ago, decided against negative numbers in here, and also the possibility of this being equal to 1 is the following. First, let's deal with this constraint. What would happen if a equaled 1 in this equation, in this function, I'm sorry? Well, I would have this, right? 1 raised to the x. But as we know, when we raise 1 to any exponent, it doesn't matter which one, I'm always gonna get 1, right? 1 raised to an exponent is just going to be 1, no matter what the exponent. So if I allow a to be 1, this function is gonna get reduced to this function, which is really very, like, not important, or not it's so simple, so banal. So I just discard it. Okay, I don't want to work with the number 1, because if by doing so my exponential function loses all its meaning, and it's going to be reduced to just a simple number. So I don't allow a to be equal to 1. That's the first thing. That's easy to understand. Now this is a little more complex. The second one: why am I refusing a to be less than 0, or negative in this case? Well, let's see why. What would happen if I allowed a to be negative? Let's suppose I give it the number -2, and let's suppose that I try to work with this exponential function, f of x equals -2 to the x. Let's see what would be the consequences of trying to do such a thing. Okay, so by doing this, I'm gonna get in trouble, because, for example, if I tried to evaluate this function in 1/2, in x equals 1/2, what would happen? I would get -2 raised to the 1/2. And remember that when we have an exponent in this way as a fraction, what this means really is a root. In this case, a square root. You remember? So this is equal to the square root of -2. And tell me what the problem is with this number, the square root of a negative number. Can we perform that? Is this a real number? No, right? So by trying to do this thing, by allowing a to be a negative number, we may run into this problem. And not only with 1/2, with any other. For example, let's suppose I want to evaluate in 3/2 this same function in 3/2. I'm gonna get -2 raised to the 3/2, and if you remember, this is the same as the square root of -2 to the cube, and then this is gonna be equal to the square root of -2 to the cube is gonna be -8, and I have the same problem. You see, I have the same problem. I'm gonna end up with the calculation of a square root of a negative number, which is not a real number. So I'm gonna run into a lot of problems, and these are just two of them. Okay, 1/2, 3/2. There's an infinite amount of numbers of x that I would have problems with by allowing a to be a negative number. So mathematicians, being simple-minded people, in the sense that they don't like to complicate themselves. I always tell that to people. People think that mathematicians like to complicate things. No, they don't. And they decided, okay, we're gonna exclude that possibility, because we get into calculations of complex numbers and so on, and we're just gonna decide for this constant a to be only positive and different than 1. So that is the reason, guys. So second point done. Perfect. I'm sorry, this is number 3. I want to it's very quick. 1, 2, 3, 4, 5, 6, and 7. 7 points. Okay, number 3, the domain and range. Very, very simple. Look at this function. F of x equals some constant raised to the x. Well, what's going to be the domain? The domain, remember, is all the numbers of x that I can evaluate in the function. Okay, all those possible numbers of x that are acceptable by the function. So when I raise a number which is positive to any number x, I'm always gonna get a good answer. Okay, the function is not going to crash. Remember that so far the only types of crashes we have when we get the domain is basically division by zero or calculation of square roots of negative numbers. Since this is not the case, this is perfectly fine. Okay, so the domain of function f is going to be all the real numbers. That's it, all the numbers. There are no restrictions. Any x will work. Now the range, how do we calculate the range, or how can we see what the range is? We resort to the graph of the function, right? Which is about time to look at. So I'm gonna ignore this for a moment and let's go to this software, Desmos. Okay, so in here I have several exponential functions. You see, one with base 2, one with base 3, base 4, and base e, which we're going to talk at the end. So take a look at the graph of the function. Okay, it's this blue line. It goes this way, and again, like I told you before, it looks as though the graph is touching the x-axis, but really isn't. If you zoom in, you see, it's not touching it. It's not touching it. It's getting close and close, but it never touches it. Okay. Okay. So by looking at the graph, how can we calculate the range, or how can we find the range? Very simple. Remember that I told you that the range is obtained by looking at all the values in the y-axis, or the axis for the values of the function that are swept barridos by the graph of the function. And if you notice, the function goes upwards. So basically all the numbers above the x-axis, okay, all these numbers from 0 and not counting 0, okay, not counting it, all the numbers greater than 0, all of these numbers are being swept by the graph of the function. All the numbers greater than 0, okay, and that's how we find the range. So basically the range will be all the numbers y such that y is greater than 0. Or in other words, since remember that the y-axis works at your axis of f of x, then the range is simply all the numbers f of x such that f of x is greater than 0. So this is the domain, this is the range, these are two different ways to say it. It's the same thing. And we're done with the domain and range. Now let's go to zeros, or the roots of the function. The zeros. Just by looking at the graph, let's go back there. Just by looking at the graph, you can see that this function has no zeros. Why? Because the graph of the function never actually touches the axis, right? The x-axis. If you notice, like I said a moment ago, the graph only approximates or approaches the x-axis, but never really touches it. Can you see? No matter how much you zoom, the blue line of the graph never touches the x-axis. And remember that the zeros of a function are those numbers in the x-axis that the graph cuts. You see? It never really touches such line. So basically this function has no zeros. That's it. It has no zeros. Okay, so there are no zeros or no roots. Done. What about the intercepts? What about the x-intercept and the y-intercept? Are there any? Well, clearly there are no x-intercepts. Remember that the x-intercepts are the same as the zeros or the roots. They are the same thing. If there are no zeros, then there is no x-intercept, as I showed you just a few seconds before in the graph. Now, what about the y-intercept? Is there any y-intercept? One more time, look at the graph. Yes, we have a y-intercept, which is this. It's the point 0, 1. You see? So we know that there is in fact a y-intercept. The y-intercept is 0, 1. Now, suppose that you don't have the graph. How do you find the y-intercept? If you remember, the y-intercept can be found by this is found by making x equals 0, or basically by evaluating your function in x equals 0. That's how it works. If you can find a number such that this evaluation is possible, then the function does have a y-intercept. So let's work that one analytically. F of 0, okay, equals a to the x. I'm sorry, a to the 0, right? I'm evaluating in 0. F of 0 is equals to a to the 0. And how much is a to the 0? Any number raised to the 0 will be 1, right? So f of 0 will be 1, and therefore this is your y-intercept, like we said before. You see, it's 1, 0, 1. So that's the y-intercept. And it's going to be the same independently of what base you use. Base 2, base 3, base 4, base e, base whatever. Look, I'm going to show this one, this function. You see? This new function, which is f of x equals 3 to the x, another particular base, also has the same y-intercept. What about f of x equals 4x? I'm sorry, 4 to the x. You see? Same y-intercept. Because what I did a moment ago, if you noticed, I actually didn't give a any value. Okay, I made the whole thing analytically. And by doing so, I found that always the y-intercept will be 1, the point 0, 1. So that's it for the intercepts. Now let's go to the asymptotes. Again, one more time, the best way to find them is just by looking at the graph in any software or any calculator or whatever. So just look at the graph, guys. Okay, same first function, f of x equals 2 to the x, and tell me whether there is a line, horizontal or vertical, such that the graph of the function approaches such line more and more and more, but without touching it, just getting closer to it. You see? It's pretty clear, right? That the x-axis acts as the asymptote of our function, and that's going to be the case always for the exponential function. You see, let's erase this one. What about this? You see, it's the same. The x-axis is also the asymptote for this other exponential function with a different base, and the same for the rest. So indeed, we have an asymptote, and that asymptote is the line x equals 0. This is the asymptote for any exponential function of this form. Okay, and we're basically done. The only thing that we have In order to conclude, the lesson is number 7, which is the natural exponential function with base e. So probably by now you have heard about this number, the number e, which is also known as the Euler's number. I'm gonna write that thing. Euler's number, el número de Euler. Euler was a mathematician which baptized this number, number e. Okay, so what is this thing? What is this natural exponential function? Okay, the natural exponential function is this. The definition is pretty much the same as this. The natural exponential, I'm gonna abbreviate a lot, function is given by f of x equals the number e raised to the x. That's it. It's that simple. So basically, if you notice, this new definition for the natural exponential function is basically just like this one, with the specific case that I'm making a equal to this particular number, to the number e. Now, how much is that number? That number for us will be approximately 2.7. You know, that's enough. There are many more numbers. I think the next one is 8. Maybe I'm making a mistake. But 2.7 is already a good approximation, okay? That's it. Actually, let me confirm because I don't want to be telling you lies. I have never memorized that number. It's 2.7 something else. Let me consult here. 2.71. 828, etc. Okay, it's like pi. It has many decimals which are not periodic, so it's an irrational number. Okay, I'm not gonna tell you much about this number right now because I want to give a whole class about this number, and it's not gonna be a bonus, like it's gonna be a normal class, because this number, guys, is extremely interesting and it's extremely important for both scientists and mathematicians and engineers and economists. You know, this is one of the most important numbers in mathematics. It's just like pi. You know, pi is one of those numbers that come up very frequently in nature, everywhere. The number 0 is also very important. The number 1, the golden ratio, as you already may know, some of you, because you worked in with that number in the IA, and so on. So basically, what is E? It's a constant close to 2.7. I made a mistake, right? It was 2.71. Yeah, that was the reason I looked it up. 2.71. Okay, and that's it for the moment. That's it. It's just a constant, which is irrational in the same way pi is. It has many, I mean, not many, infinite decimals. Okay, and those decimals are not periodic. So it's just a list of numbers without any pattern. That's it. That's what I'm gonna say to you right now. We're gonna explore this number in particular in either the next lesson or the one next to it. And that's about it for today, guys. That's enough information for today. And let's go to the exercises. Thank you.